you everyone for having me this morning. I want to talk about abstractions, specifically how they come into being and their life cycle. The reason why I thought it would be a good idea to talk about it was often enough people end up getting stuck with the kind of abstractions that were in vogue when they entered the industry, and or whichever abstractions gave them the most momentum in their career. What happens then is that as that abstraction fades away, they find themselves stuck and difficult to stay relevant. Understanding why and how these abstractions evolve gives us an edge, giving us the ability to adapt to these changes. That's the reason why I thought this would be a good idea to discuss. The talk is broken up into three parts. We'll go over the history of some of these abstractions, both in software and hardware. We'll go through, we'll review some of the kinds of abstractions that are changing right now and why they're changing. And in the process, we'll get a glimpse into the patterns that lead to changes in abstractions. Thirdly, we'll discuss how to stay on top of these changes. So let's start with the history. But to discuss history, we should first discuss definition so that we are talking about the same thing. I'm going to define an abstraction as this: a simplified way of thinking about something complex by hiding unnecessary details so that we can focus on solving the bigger problems. As you can guess, there's a whole bunch of technologies that fit this definition: programming languages, frameworks, runtimes, even command line tools like Git. So let's unpack this definition. There is exposing the higher primitive, which is about giving us the ability to reason at a higher plane. And there is a hiding of the lower primitive, so that we are not distracted by the details. As a natural consequence of this hiding part, abstractions make choices and trade-offs, which naturally means there's a cost. And by understanding these abstractions, we develop a better understanding of what these costs are. For example, in JVM, there's no way of directly managing memory, right? Short of JMI. So that's the trade-off. We get some higher primitives, but we lose control of some of the lower level details, and that cost needs to be better understood. The point is that understanding these trade-offs and understanding the why behind these choices, we develop enough knowledge to determine when these abstractions stop being useful. Let's talk a bit about some of the abstractions that had massive impact. There's a slide that I copied from a blog post of mine. The QR code links to that, where I talk about the most important software abstractions. This is my definition of importance. Yours could be different. In the past 2 decades. Let's go over a few of them. The first one is the invention of the smartphone. So iPhone in 2007. If you think about it, that's not exactly a software abstraction, but the launch of App Store in 2008 was. What it meant was that suddenly consumer behavior went through a massive shift. People were accessing internet on top of their toilet seats, when their behavior prior to that was completely different. Okay, what that meant in turn was that every company out there absolutely needed to be on the internet to reach these customers. Okay, so that drove a massive demand. The next abstraction that made a massive difference was Node.js and JavaScript. Okay, a lot of you must be wondering why I'm talking about JavaScript in like 2009 to 2011 kind of time frame when it was invented in the mid-90s. The reason is this was the first time that JavaScript actually became a full stack language. Okay, so you could actually make effective server-side programs using JavaScript, and that led to a phenomenal change in the accessibility of server-side programming. So regular programmers who didn't know how computers work could actually build full stack software. The third change is GitHub, the launch of GitHub. Git was in existence for prior to that, but GitHub essentially made it super accessible, particularly with its revised implementation of PR in August 2010. That model of pull requests effectively made collaboration a lot simpler than what it was. Open source had been in existence for a really long time, but it was GitHub that essentially significantly communitized it. Okay. Lastly, availability of cheap compute. Cheap is, arguably a contentious word here, now that all of us know the reality of cloud. But what this meant was you didn't have to own or rent a server. It would actually, so your incremental cost to play around actually became a lot lesser. Okay? So notice how all of these changes happened in a really tiny span of time. Okay? The effect of it was a massive increase in accessibility of technology. So anybody with no background in how a lot of these technologies work could just train themselves on these technologies because of the kind of demand created by the invention of smartphone. You could actually find very gainful employment and very profitable employment just by knowing how to program. And progress in technologies like Node.js, JavaScript meant that you could program more and more. You could add a lot more value just by knowing how to program. All right. This kind of accessibility, these kinds of abstractions, were so powerful that it developed a wall that most people who entered the industry in this time frame actually didn't have to cross. They didn't have to climb that wall in order to understand how things actually work. So that leads to a certain cost. One of that cost is something that I want to mention here. There's a very nice paper by the name Scalability, but at what cost? Now, I want to be very clear. Cost here is an acronym. Okay, it's not the commercial cost per se, but it's for the purpose of this discussion, it's analogous to it. Its full form is configuration that outperforms a single-threaded implementation. Okay, a competent single-threaded implementation. What the authors essentially talk about is that you've got a system A, which is a scalable system, which has been created. A system B that is actually optimized to really extract the full power of the hardware. Okay. A always performs significantly worse off than B, but A scales much better. By scaling, there's a quote in there. It is always poorer off. At no point in time does A outperform B, but A is scaling better. The point is, A is scaling because of its poorer choices. Okay? B, which is an optimized version, doesn't scale. If you see, B actually flattens out in the first graph. Okay? B doesn't scale. Okay? A is giving you the impression of scaling, but when in fact A is actually a poorer performing system. All right? So this is a very common thing that actually started happening, where scale, the notion of scale became sort of a little decoupled from deep systems thinking. Okay? In fact, it's summarized in a very nice quote by Paul Barham. You can have a second computer once you've shown how to use the first one. Okay? So this is the kind of effect that massive increase in accessibility has. And just to be clear, I'm a big fan of increase in accessibility of technology. I'm a beneficiary of it as well. But these are the costs that we should be talking a lot more of now. Okay? Next, let's talk about abstractions having a half-life. Now that we've covered a little bit of some of that history, remember that abstractions come into existence by virtue of the trade-offs that they make. So when the assumptions behind those trade-offs actually goes through a change, naturally there's a change in the circumstances of that abstraction's relevance as well. Okay? For example, let's talk about threads. Threads as a primitive is something that gets used for parallelization, which naturally extended it to talking about concurrency as well. Right? Some of you might have be familiar with the difference. Might be familiar with the difference between concurrency and parallelization. Okay. So thread became a very dominant concurrency primitive. The idea was simple. A process would spawn a bunch of threads. A thread would keep on continuing until it yields, either by virtue of doing an I/O or by having its time slice getting sort of suspended by the scheduler, right? The scheduler would kick in. There's a cost to that, and then the next process is actually going to get scheduled in. All right. This works quite fine until you start having massive levels of concurrency. Okay. Let's actually figure out why that is the case. Let's say in this scenario, this diagram is not to scale. The first time slice that was given to the process was 5 milliseconds. Then there was a 5 microsecond cost to switch and another 5 millisecond of scheduling. Efficiency, 99.9% useful work. Right? Now let's say we've started using threads as a concurrency primitive. So I've spawned a huge number of threads to deal with the massive level of concurrency, each thread doing only a tiny amount of work. Okay? A thread did like 5 microseconds of work because the work got completed and I'm waiting for I/O right now and the scheduler kicks in. Efficiency, only 50% of the time useful work is actually happening, right? This is the kind of issue that happened when the levels of concurrency went through a massive shift. So threads' relevance as a concurrency primitive fundamentally changed, okay? So to solve for it, what we did was we came up with user space, cooperative multitasking. Okay, where in the time slice that is made available, the kind of library or the runtime makes it easy to do a whole bunch of different things and actually go through the time slice to completion. Because that's the only way we can actually extract a lot more efficiency from the hardware. All right. So threads as a concurrency primitive got replaced with user space cooperative concurrency primitives. A change in circumstances leads to a change in abstraction. This is a very, very important thing that we'll keep exploring in this conversation. Okay. So with that, let's get to the last slide of the first part. We'll talk about the hardware abstractions and the history of that. Okay. Let's start with looking at how performance of each one of these things evolved over time. Let's start with CPU. Okay. Around 2004 was a very interesting year because just a year prior to that, 2003 is when AMD launched 64-bit, the first 64-bit x86 processor. Intel sort of followed that up with that later. And in 2004, they actually introduced the dual core, the first dual core CPU. Okay. So since then, so we are currently 2024. The average performance of the CPUs now is around 64 times more than the average performance of CPUs in 2004. Okay. The sort of data points around this, the slides are available online, and you can look into this slide in the comment section. I actually have linked to the data points for this. Okay. So 64 times. Now let's look at how the single threaded, the single core performance improved. 8x. It doesn't look much, but it's 8 times. Okay. Moves from 1 in 2004 to 8 in 2024. Okay. So single core didn't move, but like it's almost flat as compared to the overall CPU performance. It means that largely we've gained performance by increasing the number of cores, increasing the amount of parallelizability. Okay, that's been the history of CPU's evolution. Let's talk about I/O. I/O has also sort of grown, like almost sort of managed to grow at the same pace as CPUs. And the reason is using a technology called PCI Express. So PCI 1.0 I think was launched around 2004, 2005, and we are currently in PCI 5.0, which gives us about okay. I'm very glad there is some video going on in the background. Sorry. So IO has managed to keep keep up with the CPU's growth. The reason is PCI Express is a very scalable technology. You can keep adding lanes, and you get that much more performance. Okay, so we are currently in PCI 5.0. Let's look at memory. Now memory doesn't seem to have grown as much. Sort of went hand in hand for some time, but in the last, I would say 10, 12 years, it's really fallen behind. The amount of change from 1 in 2004 to about 32 in 2024. Okay, so memory has lagged behind, and the reason is we don't have sufficient time to get into the difficulties of increasing the number of channels of memory. But we've tried a few things. For example, in 2014, 2015, we came up with a technology called HBM, high bandwidth memory, which is like you develop that by literally 3D stacking memory on top of the CPU die and dropping, conducting wires onto the CPU. But that takes up a higher cost, so it largely ends up getting used as a last level cache or as memory for GPUs. For your main memory of like 512 GB or 1 terabyte of memory, those things are still accessible with a much more reduced bandwidth. The important thing to bear in mind here is that because of this change, the relative cost of memory access is a lot higher today. Is that obvious? Right? CPU's performance has gone up. Memory bandwidth has not kept pace with that. It's grown slower, which means every time I'm waiting for memory today, for every microsecond that I'm waiting for memory today, I could have done a lot more work today than what I would have been doing in the same time 20 years back, right? So the relative cost of memory access is a lot higher. Sorry?
I mean, what's the difference between memory and I/O? Like both are same, huh? I/O is memory access.
No, so I/O memory access is when CPU essentially reaches out to memory and says that, okay, give me the value of this variable or the value of this array or something like that.
You mean?
Memory access is the RAM. I/O is when you are, say, for example, doing network, or you are hitting the disk, or anything that is going via PCI Express. The key difference is memory access for CPU is uninterruptible at a software level. So when CPUs issue an I/O instruction, they inform the kernel, and the kernel can suspend the process that did the I/O until I/O is available and schedule in another process. So we have the ability to use I/O time efficiently. The kernel gets an opportunity to use CPU efficiently. In case of memory, the kernel is not informed. Okay, CPU does some optimizations internally, but often enough, CPUs actually in most servers today, in most of the applications that all of us build here, most of the time CPU is actually spending waiting for memory.
But still, memory is faster, right, compared to I/O?
Memory is faster. That's why I'm using the word relative cost of memory is a lot higher. Okay, the relative cost of memory access is a lot higher today, substantially higher. Okay. All of us good with that? Okay. So with that in mind, let's look at a few emerging trends. Now these are trends that I have picked up. Only so treat them as indicative, not exhaustive. I'm sure that you guys can think of a whole bunch of other trends and abstractions that are going through a change right now. Okay. Let's start with pervasive use of VMs, virtual machines. I'm going to use two examples. First one is eBPF. Anybody here who's familiar with it? Okay, a bunch of. All right. So how did eBPF start getting pulled into the kernel? We've got network side, right? Okay. So you have packets coming into the system, and there's a bunch of processing that the kernel does, and then it passes those packets to the processor. Now remember, relative cost of memory is higher today. Okay, so let's say that packet was not relevant and you wanted to drop it. or let's say that packet was actually not destined for this machine, it had to be shipped out to another neighboring machine. Okay? All of these changes are unnecessarily going through a cost of what is known as a socket buffer allocation that the kernel does. So the kernel is touching the memory. It's doing some dynamic allocations, which has a much higher cost today. Okay? So instead of that, we actually create a small virtual machine program, and that virtual machine has really tiny set of opcodes designed for security. And we can plant that right when the packet is entering is being received by the kernel. Before the dynamic allocation of memory is done by the kernel, our program gets to read and act on that packet. Okay? A consequence of relative memory access becoming a lot costlier. All right? And eBPF obviously is a lot more flexible than that. It's actually far more pervasive in the kernel than just the network. But I wanted to give a sense of the kinds of things that start happening when relative cost of memory access essentially goes up. Okay? The second VM that I want to talk about is WASM. Modern browsers are full-fledged computers in their own right. All of us would agree with that, right? But the kind of runtime and language that we use to build on top of it, the JavaScript has no ability to give you control over memory, right? It's designed to be safe, designed to be accessible, okay? Browsers are capable of much more than that. So what people did was, they came up with a virtual machine where your program at a machine code level can actually access any part of the memory directly. Okay, so flat addressable memory is possible, which is not possible in JavaScript. Okay, this kind of a VM being embedded in the browser gives us the capability to have C programs being compiled to WASM and deployed. Okay, because cost of accessing memory is higher, we want to be very particular about when we touch memory and where we touch memory. We don't want memory to be fragmented all over the place. We want to be touching only contiguous memory. All of these things are possible only if you are writing in WASM. You just cannot actually implement these kinds of access patterns in JavaScript. Okay? So WASM is another one. Again, WASM is not limited to browsers. It developed a life of its own, and we'll see more use of it outside of browsers as well. Okay? Shift of concurrency primitives I've already talked about, but I do want to talk about one thing, the context switch cost that we were discussing earlier. Because the cost of memory access has gone up, the relative cost of context switch is higher today than it was 20 years ago. Why? Because context switch, the largest component of it, is actually the time needed to walk through your page directory and stuff like that. Right? So the cost of memory access is what actually makes context switch a lot slower. Which means that if the relative cost of memory access has gone up, the relative cost of a context switch has actually also gone up. Okay? So that's something to bear in mind. But otherwise, I think we've covered this already. Another change related to the cost of memory access going up. A shift in the kinds of programming languages that we write. One example that I want to talk about is Zig. A few of you, anybody who's heard of it here? Okay, a bunch of you, right? Zig actually takes a very extreme approach. It has a notion of explicit allocators. Okay? So if your function does any dynamic allocation, it will show up in the signature of the function. Just like a few languages have this notion that if you're throwing an exception, it has to show up in the signature of the function, right? Because the programmer, in the programmer's reasoning plane, you want them to be mindful of that reality. Similarly, in case of Zig, because the cost of memory access is so much higher, you want anything that allocates to be explicitly noted as such. Okay. Yet another example is Rust. Okay. Rust takes a very different approach. It takes a memory safety approach, which on its own actually doesn't have anything to do with the cost of accessing memory. But the kinds of things needed to guarantee that memory safety via its ownership model, a side effect of it is that the number of times you are touching memory essentially goes through a chain, often reduces. which means that often enough, if you were to rewrite something in Rust, often enough, no guarantees, it would be faster. Okay, and almost all of it has to do with the number of times you end up touching memory. All right, and with all of these programming languages, these are very modern programming languages. A whole bunch of software is being rewritten. A bunch of you would have heard about Bun, right? So arguably it's much faster than Node in a lot of different cases. Similarly, there is one software in particular that I want to talk about, Tiger, which is written in Zig, but it's fascinating in its own way because it claims something massive. It's a ledger database which claims that for ledger use cases we are 1,000 times faster. 1,000 is 3 orders of magnitude faster than if you were to be using a regular database to essentially build ledger-like use cases. All right. And the reason why I want to talk a little bit about why I thought talking about them would be relevant in this session. Obviously, one of this is no dynamic allocation. Okay, we've talked about cost of memory, etc. That's not the only reason why I'm talking about Tiger. Okay, well, they definitely do memory stuff, things related to a higher cost of main memory access by not doing dynamic allocation altogether. Now, if some of you think that not doing any dynamic allocation would prevent scale, you were not paying attention to the slide on cost that I showed earlier. Okay, a single thread implementation can be massively competent today. All right. But that's not the main reason why I'm showing Tiger Beetle here. The first main reason why I'm showing it here is that the primitives that they expose is not your standard row grunts that databases expose. The primitives that they expose is a debit-credit primitive. Because they are designed for ledger, the primitive that they expose to the programmer is actually reflective of that domain. And what that allows them to do is it allows them to work their way back across the abstraction and reinvent every layer, hidden behind the stack. Okay. What they do is they optimize the system as a whole. Normally, how do we build software? We pick parts, we pick components that are quite optimized. Say, for example, a HTTP library or some consensus library. Okay, and then we assemble them together, almost in a Lego-like fashion, right? So we assemble after optimization. These guys do the exact opposite. They pick every abstraction, completely break it apart, and essentially optimizing how the system is performing as a whole. The founder of Tiger Beetle has given a very nice talk on it, which I strongly recommend you guys go through. This is in that QR code. Optimizing this system as a whole is the reason why for every query, they do, at least that's what the CEO claims, they do, I think, for every query, 4 system calls, 4 memory copies, and 3 network tables. That is how they are tracking. They are thinking in ticks across each component. That's the only way you can optimize to this level of performance. If you just assemble together a bunch of different components, you cannot achieve this level of performance thresholds. All right. So I thought I'll share this because I expect a lot more of things like these to be happening, where people are optimizing the system as a whole instead of just simply doing a Lego-like assembly of components. All right. My last 2 examples for change of abstractions are not related to memory access, because I didn't want to convey this impression that there's a memory kind of talk. The first one of these 2 is massive parallelism related to GPUs, NPUs, whatever it is that you want to call it. Massively parallel processors are already there on our devices, right? All of us have GPUs and modes on the way in the form of NPUs. They present a programmable abstraction that most of us aren't thinking about as much right now. This is a slide from a lecture I conducted on GPU architecture to dispel some of these myths. When I ask people what is faster, CPU or GPU, most well-informed people would say it depends. Okay? But if I were to ask, by how much is a single CPU core faster or slower than a GPU? Any guesses? 5x? 10x? Okay, so I did this thing. Okay, I did a min parallelization, and CPU took 15 milliseconds for the job, and a single GPU core did, like what this is, 90x of that time. That is the amount of the degree to which a single GPU core is slower than a single CPU core. Okay? And the QR code has all the details to that, so you guys can do this test for yourself. This was on my MacBook Pro M1. All right? The same thing, if we were to do mass parallelization, we are engaging all the GPU cores, the GPU is faster by about 19x, I think. Yeah, 80-90x or something. Right? Okay? So it's not about the performance of a single core, it's about how we actually engage. All right? This notion of throughput being used to hide latency is actually a very, very common pattern. There's nothing new to GPUs, it's been in existence for a really long time. And the reason why I'm talking about it is because is massive parallelism restricted to graphics or AI or things like that? Can we not think about day-to-day use cases? A lot of what we end up doing actually to program something like this. The programming paradigm is actually substantially different than how the normal imperative programming that we're used to. Okay? It requires a different programming model, but if we adapt to that kind of a mindset, that way of thinking, we would actually start identifying opportunities that very few people are identifying today, and we can actually do a lot more. This is something that I expect would actually become a very common phenomena, and a lot more software engineers will need to be familiar with the programming models of things like this. Lastly, the last abstraction that I want to talk about is AI. A lot of us don't really think about AI as abstraction per se, but if you think about it, it fits our definition very neatly. It exposes high primitives. It's in the form of, let's say, token prediction as a reasoning plane. That is the higher side primitive. And it hides away the lower primitives. For example, the exact logic that is used to determine an outcome. As an example, one could deploy an LLM as a particularly costly classifier, right? And something that required dedicated data scientists to be working on can now be deployed by a regular person. Of course, the costs are going to be higher, but if you were to include people and time costs as well as the decreasing cost of NPUs over time, the equation starts looking very different. So AI as a computable abstraction, I strongly suspect we'll see a lot more of. Not just as a tool that the way that as an assistant that we use it today, but as a quite literally a programmable abstraction. It will actually show up in a lot more programs, and we'll be using a lot more of it in terms of how we actually build software. All right. So that was the end of part 2. We come to the smallest part of my talk. This is preparing ourselves. Richard Hamming, one of the greats in our field, said this: education is what, when, and why to do things. Training is how to do it. Either one without the other is not of much use. Okay? I think this is a very relevant quote when we think about how increase in accessibility of technology allowed a lot of people to become productive just by training themselves. Just how to program, and that is sufficient, okay, to add value. But as we get into the next stage of systems building, I strongly feel we'll see a lot more of the need for understanding the what and the why behind things. Another reason for this is, as we dig deeper into the what and why of anything, it could be, let's say you are a web developer, or you could be a so-called backend developer, or so-called database developer. No matter which point you use to enter, the deeper you dig, you would realize there's a fundamental homogeneity to knowledge. Okay? We are all talking about the same things. It's just that the trade-offs that each one of those things are making is different. So you start from, let's say, web dev, go deep, you emerge into the database side of things with 80% of the knowledge already being there with you. That's how knowledge works, and that is a major takeaway that I want all of us to have. That foundations, going deep into the foundations, or helps us deal with this a lot more effectively. Okay. So summarizing my talk, abstractions are useful, but they can create walls. Understanding the why behind the abstractions helps us understand their half-lives, so that we know how to walk away from them at an appropriate time. Yeah, and foundations help increase longevity. Technology changes fast, but foundations remain the same. That was what my talk was about. I am hoping that at least a few of you will use this as an opportunity to rethink the abstractions that you use and think about what kind of changes can be made. Thank you. Yeah.
We have a mic, I think, somewhere.
Will you be taking questions?
We have 10 minutes to take.
Okay, we have 10 minutes to take questions.
There is a mic, no? There.
I'll be done. Hello. Yeah, I have one question regarding the tiger beetle example. I think you mentioned that they broke the abstraction so that they have the necessary control to optimize at the lowest level of granularity, right? So isn't this a cost on the maintainability side of things? Now, anyone who comes to start working on a project like this, they have way too many concepts to understand before they can even get started.
100% true. Okay. In fact, something that I should have mentioned is that a choice like that is possible only with the very clear understanding that your average engineer out there who's working with you is familiar with a large variety of these concepts. Okay. So this heterogeneity in sectors is a crucial element. The good part is what I mentioned in my later slides, that a good engineer, actually because they go deep into the foundations, their understanding of all of these different sectors is naturally very good. Okay? And here's another way to think about it. I feel that Lego-like assembly of products is going to become easier and easier and easier to the level where the value that you can extract by Lego-like assembly is going to keep reducing because everybody can do it. Okay, so as engineers, how do we think about higher value creation? Fundamentally, we'll have to walk away from a Lego-like assembly. We have to think about systems as a whole. This is not the only way you can walk away from Lego-like assembly, but this was just one of the possible ways. So food for thought, that Lego-like assembly is going to yield much lesser return for you. Any other questions? Yeah.
So, thank you for that memory versus cache trade-off. Because this is what I see a lot of, in fact, CPU manufacturers are adding more and more layers of cache in larger caches. And it never clicked to me in that way. But that chart retrospectively looks very nice to see and it's very self-evident. But what's your opinion? Can we foresee such things coming up?
Yeah, I think can we foresee, it's a difficult thing to comment on. I think, but there's signs that can be seen. Okay, let's say, for example, HBM as an example I was giving, right? Heterogeneous computing. Heterogeneous computing is a term that we often talk about, where on a single CPU die, you have very different characteristics of cores and memory that is available on the same die. Okay. For example, performance versus efficiency cores, or integrated GPUs, unified memory is another example of it. Okay, so that kind of a pattern you can see that we'll see more and more of. Okay, to what degree it sort of takes off is very difficult to predict by nature of it. Otherwise, the person who's doing it is like super rich, obviously.
Yeah.
But at least we can see signs, we can discuss amongst ourselves, we can share what we believe, things like that. I feel that there's a lot more conversations we should be doing regularly about the why behind things. So things like these, conversations like these, help us reassess what we want to build and how we want to build, right? So more conversations like these just sparks more thoughts, and hopefully it converges into something close to your answer.